Hello, everyone. My name is Chao. I'm a research scientist at AIP Center, RIKEN Institute. In this presentation, I'm going to talk about the notion of tensor network, and we'll focus on its model selection problem, which is new and crucial to affect the performance of tensor network in the application of machine learning. The studies on the tensor network are mainly motivated by the problem called dimension exposure, which happens almost everywhere in the field of machine learning. So to address this problem, we borrowed the idea of tensor networks from the field of quantum mechanics and found that the tensor network is a promising framework to deal with high-dimensional problems in machine learning. Well, so in this presentation, I will first give a brief overview about tensor networks and its application in machine learning. And then we will talk about the targeted problem in this presentation, the problem of tensor network structure search. And at the end, we will give our solutions to this problem to show how to find the optimal tensor network structure via random sampling. Well, let's start with the concept of the tensor network. The definition of the tensor network relies on a fundamental mathematical object called tensor, which is intuitively a multi-way number array. In the context of tensors, we can consider vectors as tensors of order 1 because there's only one index for locating their entries, and consider matrix as tensors of order 2 because there are two indexes corresponding to rows and columns. And here, when we say tensors, we commonly mean the ones with higher orders. And then on tensors, we further define an operation called contraction, which can be understood as a natural extension of the matrix multiplication. The tensor contraction amounts to the tensor multiplication. And to simplify the notations, tensors and contractions can be also represented by graphs. Here, we use the vertices with multiple downlink edges to represent tensors with different shapes. So based on these concepts, the tensor network is thus defined as an edge-labeled graph, of which the vertices correspond to tensors and each connected edges indicates the contraction between the two linked vertices. So we can see the tensor network can be used to describe a sequence of complex contractions among many tensors. Well, now we know what the tensor network is, so let's move on to the next question, how to use tensor network in machine learning. Suppose we have a learning equation as shown in the slide, where x is the input, y is output. The w here denotes the learnable parameters, and the phi indicates any linear functions requiring the learning task. This learning equation is so simplified, but still can be used to describe a wide range of learning tasks. And in this science, the problem of dimension exposure usually implies two things. The first is the dimension of W here is literally high. It means that we have to pay much computational resources for training or for the inferences, which might not be afforded. And the second thing is sometimes the dimension of W is not so high, but the size of the training set is very limited. This situation usually happens in the field of scientific research, and in this case, we usually suffer from the serious overfitting problem. So to resolve these problems due to the dimension exposure, the recipe of using tensor network is very simple. There are only two steps. In the first step, we need to map the high-dimensional parameters into a tensor space, and we call this step as tensorization. And then we will find a suitable tensor network to decompose the high-dimensional parameters into a group of low-dimensional blocks connected by the tensor contractions. Because the tensor network has a significant ability for model for the dimension reduction, so the two-mentioned problem will be mitigated. So to further understand this point, let's see one example that is the problem of tensor completion. The goal of tensor completion is to predict the missing values of a tensor from the observed entries. And it has been successfully applied to the tasks such as recommendation system and image imprinting. And we know that the tensor completion problem also satisfies the mentioned learning equation. But in this problem, the x are coordinates of the entries, y are values of the entries, and the w here correspond to the completed tensor, which is our target. And the function phi is usually just the identity, and sometimes it's a reshaping operation. And in practice, we usually have to be faced the situation that is only very limited entries can be observed. So the tensor completion usually suffers from our fitting problem. So to resolve this problem, what we did by tensor network is just as what we have mentioned. The high-dimensional parameters will be replaced by a low-dimensional tensor network. Here we use a tensor train format corresponding to the path graph, for example. Because we have known the tensor network can be used to describe a sequence of multiplications of the low-dimensional tensors. It means that this trick can successfully transform the high-dimensional original problem into some low-dimensional latent space. And so, as the result, our fitting problem will be solved. And the tensor network also has rich applications in deep learning. And the goal in this application is mainly for model compression. We can see that in the existing works, various tensor networks are applied to different deep neural networks. But on this point, we should note that even though in their works, they show that the tensor network gives remarkable performance for model compression, but there's still no principle to show if their use of tensor networks are optimal for their tasks. In other words, there's no answer for the question how to select optimal tensor network structure for the machine learning tasks. So this factor motivates a study of on the problem of tensor network structure search, or TNLS. The main goal of this problem is to looking for the optimal tensor network structures for machine learning tasks. And this is a relatively big problem which covers three specific subproblems. They are the rank section, permutation search, and topology search. To understand the meanings of these three problems, let's see another example. In this example, we try to represent the fMRI data by tensor networks. The fMRI is a sort of brain images which are naturally are tensors of order 4 because there are 4 physical indexes, where the indexes x, y, z correspond to the spatial space which contains our brain, and the index t correspond to the time space. So for the first tensor network rank section problem, here we are looking for the optimal H labels, which determines the bound dimension of the vertex tensors. And because these labels can be also concerned as the tensor network ranks, so this problem can be understood as an extension of the classical rank section problem for matrix decomposition. And for the next tensor network permutation search, here we seek the optimal mappings from the tensor indexes to the vertices of the graph, because it's equivalent to find the permutations of the vertices in a graph. So we call this problem the tensor network permutation search. And for the last one, the tensor network topology search, it's very obvious. Here we are looking for the optimal network topology, such as the circle graph, path graph, or trees for our representation task. Well, there have been many methods which can be used to solve these problems. If we consider the three mentioned problems as the three different directions for the whole tensor network structure search, there's a special area where the tensor network structures are fixed. Because in this case, the problem becomes a trivial application of tensor networks to machine learning. So there has been lots of works here. And studies on the rank selection are also rich because it's close to the rank selection in the matrix case. The studies on the topology search is relatively new, which is firstly mentioned by Hayashi in 2019 and formally proposed by us in 2020. And following our works in the recent years, some methods were proposed where they focus on searching both the ranks and the topology. And at the end, for the problem of the permutation search, the study on this problem is very new. It was formally proposed also by us just in this year, but actually, this problem has been conceptually discussed by tensor researchers for a really long time, and in the most recently, Chen and their co-authors from Duke University theoretically proved that the optimal permutation for tensor train and tensor ring is identifiable. And the involved techniques in these algorithms are also different. In this presentation, we will give our solutions to these problems via statistic search. We choose this technique because it is more flexible to deal with the variety of the learning from the different learning models or different learning criteria in practice. Well, to introduce our solutions, let's begin with some mathematics. As the first step, we need to formalize the tensor network structures. Here in our methods, the tensor network structure is modeled as a simple graph G with its labeling function R, where the graph G contains the information about the topology and the permutation, and the function R corresponds to the tensor network ranks. And okay. And we use the explicit definition of the tensor network proposed by Ye and Lam in 2019. We choose this definition because it highlights the importance of the tensor network structures. So based on these frameworks, the tensor network structure search for the decomposition task, for example, as to solve an optimization problems as like this. Here, the objective function can be the compression ratio or the number of parameters which is used to evaluate if a tensor network structure is good or bad. And in the constraints, the graph set GC and the rank function set FC determines the feasible set of the tensor network structures in the search. And if we can construct the feasible set with different forms, we will obtain different searching problems. For the rank searching problem, we fix the graph by looking for the optimal ranks. And in the permutation search problem, we construct the graph set as the set of graph isomorphisms so that we can search the optimal permutations of the vertices and the topology will be preserved. And for the last topology search, we usually fix the tensor network ranks, but consider all possible simple graphs in the search. And in our algorithms, we try to seek the optimal tensor network structure via random sampling. And the key point is to give a good balance between the exploration and exploration in the search space. And our algorithm mainly contains two phases, that is sampling and evaluation. In the sampling phase, we randomly draw a batch of tensor network structures with some learned sampling distributions. And in the evaluation phase, each tensor network structure will be given a score to represent its fitness in the problem. And all the informations of the scores will be used to update the sampling distribution for the next iteration. The two phases will be done recursively until convergence. And more specifically, our methods consider two sampling tricks. They are the global sampling and the local sampling. The global sampling means that we draw the samples from the whole search space. Well, for the local sampling, it means that we only sample the structure from some predefined neighborhood for some given point. And as for the updating rules of for the sampling distribution, on the global side, we apply the well-known genetic algorithm, and on the local side, we concern the zeroth order optimization. It means that we use the samples from the neighborhood to estimate the steepest descent direction to update the sampling distribution. And the two different sampling tricks have their own advantages and disadvantages. It's difficult to say which trick is better because it's just a different balance between the exploration and exploration. Well, next, let's see some numerical results. This experiment is for the natural image compression using the tensor network topology search. And the goal is to looking for the optimal, the most efficient tensor network topology for this task. And here we randomly select 10 natural images from the open access dataset and consider two performance measurements. The first is compression ratio and second is relative squared error. And for comparison, we take the tensor train and the tensor ring as the baselines, which are the two most popular used tensor network in machine learning. And from the experimental result, we can see with a similar approximation currency, the topology search algorithm always achieve the better compression ratio performance. And we can also see that the optimal tensor network structure learned by our algorithm is significantly different from the ones used in the existing literature. And the second experiment is for the tensor network permutation search. Here we applied our permutation search algorithm to 3 benchmark experiments. There are image compilation, image compression, and dimension reduction for Gaussian processes. And here we also evaluate the computational efficiency between the global and the local sampling trick. The values in the squares as the number of required evaluations by the algorithm to achieve this performance. It determines the computational complexity of the algorithm. We can see from the experimental result that the local sampling requires a significantly less number of evaluations to achieve a similar performance as the global one. To verify this point, we also check how the loss function decreased by the two algorithms with different number of evaluations. And we can see that for the local sampling, that is the red line, that is the red line, the loss function decrease consistently faster than the global one with different settings. So we can say that the local sampling is more efficient than the global one for the tensor network permutation search task. Well, at the end of this presentation, let's have a brief discussion about why tensor network structure search is so important. It is because the tensor network structures encode our inductive bias about the learning task. And the efficiency of the tensor network for machine learning also comes from here. Because of the flexibility of the tensor network structure, we can encode as much as our prior knowledge about the task into the models. But this prior knowledge can be encoded into the ranks or the graphs. But the problem is, in practice, it's quite challenging for us to know how to encode these inductive biases into the tensor network correctly. So as the conclusion of this presentation, we'd like to say our research results prove that these inductive biases can be learned from the data set efficiently. Thank you.
Okay, thank you very much. Are there any questions?
Questions for Chao here?
So then let me start. So structure search is of course a quite important problem, but always search cost is really sometimes exponentially high, right?
Yes.
And this time you focused on evolutionary strategy, and this is maybe practically useful. But can you somehow say how scalable the current approach is?
You mean the stability?
No, scalability.
The scalability. Yes. I think maybe this is depend on what kind of sampling strategy we used. If we consider use the global sampling trick, I means that the genetic algorithm is used. In this case, maybe the algorithm can only deal with the tensors with orders less than 100. But we can consider the local sampling trick, means that we only draw the samples from smaller neighborhoods. And then we estimate the kind of grading-like directions to update our search strategy. In this case, maybe the algorithm can deal with the problem maybe more than hundreds.
I see. So that means if you have some prior knowledge or some hint to focus on a particular local region, then your method can be scaled to a larger part. Okay, thank you. That's clear.
Yes.